magnetic field. We are only concerned with the electrical field. And because inside the cable, the light is traveling as a wave, it means it has some waveform. Let's say something like this. So we are only concerned about the real part. Okay. Uh, Real part of the, let's say, wave, I say expression. It would be easy when we go to the equation, then you can realize that, okay, we are going to use this expression, and in this expression only the real part is our concerned part, and the other part we just ignored, the imaginary part, the j sine theta part. So, and we only need electric field to represent the equation. I think the lag is coming in my writing. You cannot see after we only need part what I wrote.
Yeah, after that it stopped.
I don't know what is happening.
Maybe one note is better?
One note, I don't know. I always use notability. So what is happening now? Let me pause and resume. Yeah, now you can see. So yeah, so we are only going to represent the equation of light with the electric field. And what that equation is, so that's your number one formula. Okay, write it down. E naught cos omega t minus k and z. Here you have k, which is called propagation constant, and its value is given as 2 pi over lambda. So as I drew this wave here, from this point to this point, from one peak to another peak, this is the length of your wave, and this is the time period of your wave, 2 pi. So phase constant is 2 pi over lambda. So it means it's a periodic wave. Every uh, after 2 pi, it's repeating itself, and wavelength is lambda. So you have a phase constant which is 2 pi over lambda. Uh, so that's your formula number one. Number one. Omega is your angular frequency, and z is your distance. Okay, so now we are talking about the wave, and wave is energy. So it means we need an expression for energy as well. Uh, so if you have, so expression for energy is Eg is equal to 1.24 over lambda, and this lambda is in micro, in micrometers. Electron volt. How did it happen? So this is your formula number, let's say 2. How did this happen? How did we got Eg is equal to 1.24 over lambda? Uh, we got it because we know that c is the speed of light. Speed of light.
If you're writing down something, we can see it.
Oh, see now. Yeah, now you can see.
Yes, thank you.
Yeah,
Oh
so
yeah.
I'm saying that we are going to see that how we got this energy expression. Eg is equal to 1.24 over lambda. So we know that speed of light is c is equal to f lambda. So this is for this course we are not using f, we are using term nu, which is like v. Okay, so that's your frequency and that's your wavelength. And we know that Eg is equal to h nu. Okay, that's another expression. What we do is we put value of nu in this Eg expression and we get uh, h dot c over lambda, and the units are joules. If we divide this expression with uh, the charge on a particle, c over q 1 over lambda. So now this h, c, and q, these are uh, constant values. They are not going to change. Only lambda is changing. Okay. So if lambda is changing, the energy is changing. And when, let me just
Wait, sorry, what does H stand for?
Planck's constant.
Oh, Planck's
Let
constant.
me
Okay.
just, yeah, write it down, the values for you. So Q is 1.6202 into 10 to the raise power minus 90 in coulombs. H is your Planck constant, which is 6.626 into 10 to the raise power minus 34. Units are meter square kg per second. And then you have C, which is speed of light, 3 into 10 to raise by 8 meter per second. So when you put these values, uh, you get this expression Eg is equal to 1.24 over lambda. And always remember, for this course your lambda is in micrometers. So if in your problem it is given that lambda is nanometers, first convert it into micrometers and then put it in the equation. Okay, that this is very important information, and like in your quizzes, in your mid final, everywhere, only trick would be this, that you are given some different value of lambda and then you know that okay, oh no, lambda was always in micrometers. So first convert it into micrometers and then put in the equation. Okay, got it? So yeah, so that's your equation number 2. Okay, next expression is for phase velocity. So we knew that E is equal to E naught cos omega t minus kz. We just saw this expression. Now we say we know that omega angular frequency is 2 pi nu. 2 pi f, we are saying 2 pi nu. And this nu is c over lambda. Come on. Stopped. Yeah. So this omega is 2 pi nu and nu is c over lambda. So we put this here. So now if you see this 2 pi over lambda, we use somewhere, what was the expression? So can you see that propagation constant is 2 pi over lambda?
Yes.
Yeah, so we know that k is equal to 2 pi over lambda. So we put this here. So omega is equal to c dot k, which means c is equal to omega over k. And this c is your phase velocity. So if again stopped.
I think you paused again.
Yeah, so I figured out when I don't move this screen much, it pauses. Yeah, see, now it's back. Yeah, so this c is your phase velocities. So what does it mean? What phase velocity is? So imagine your sunlight or in the air. When your light is in the air, c is equal to 3 into 10 to raise per 8 meter per second. So it means it's just one frequency, one wavelength. Okay. So there are no two, three, four, five wavelengths. Like it's not like a rainbow. It's a simple light. So it's traveling with one velocity. So we don't have expression for different wavelengths. We have just one expression, one ray, one light. That's your VP, and that's equal to the speed of light. And then for VP, you just find the expression that if you have uh, uh, angular frequency and phase constant of this light in the air, you will ultimately get expression is equal to c, speed of light. So next is the group velocity, which is important. So that's your, sorry, it's number 3, 1, 2, 3, maybe number 4, I think. I don't know, let's say number 4. So group velocity. So now when you have lot of rays like with separate wavelengths going or traveling in the inside the fiber optics, you have different velocities going on. So you cannot calculate velocity of each ray at a point. What you do is you name it group velocity, like overall or the average. What is the average velocity? It's not a good term to use, but just to understand that on average, what is the velocity with which every wave is traveling. So when you are in air, your refractive index, this is a new term, but in air refractive index n is equal to 1. But when you are in a denser medium,
I think you paused again.
yeah, I'm looking at that. I'm so sorry. I don't know why this is happening.
And sir, was the third equation k is equal to 2p over or 2 pi over lambda?
So the first one was, it's totally paused. I'm moving back and forth, but it's not responding. Pause sharing. So the first equation was this, and then you had this expression Eg is equal to 1.24 over lambda, and then you have this, yeah, then you have this expression. So that's equation 3. I wrote 4.
Oh, okay. Yeah, I was wondering. So
Yeah, so that's equation 3.
I have a quick question.
Yeah.
Do you mind posting this somewhere after you're done?
Posting what? The notes?
Yeah.
Yeah, I'll email everyone. I cannot post it on D2L because other sections, once I'm done with them, then I'll post. But I will separately email you this.
Okay, thank you.
Yeah. So the group velocity, so when you are in the air, you have n is equal to 1. So let's say you have n here. Okay. Let's name it n1. N1. So this is 1, so it's not going to make any difference. But when you are in a denser medium, which is greater than 1, again pause. Yeah, so when you have a denser medium which is greater than 1, it means this C over N1 is going to, so this increase in N1 is going to reduce the velocity. Okay, so it means you have Vg is equal to C over Ng in whatever medium you are, is going to impact this. And this is equal to the partial derivative of omega over phase constant K. And that's your equation number 4. Okay, so these two expressions are very important. So so basically this is your light in air. Okay, then you have a denser medium. Now your light is going in a medium which is greater than 1. Okay, so when you are moving from air to a denser medium, few things are changing and few things are remaining constant. And let's say see what these things are. So when you are in n is equal to 1, I just extend it. Your C is, let's say, C naught over n. Let's say this is n1 and this is n2. So your C is your speed of light, same 3 into 10 to raise power 8. But when it goes into the denser one and you divide it by 2, it means this reduces. Okay. What is next? Next is frequency, nu. nu does not change, then you have angular frequency, which is your 2 pi nu. Okay, and this is, as nu is not changing, this is not changing, so does not change. Then you have phase constant k, which is 2 pi over lambda. So when you are moving from lighter region to the denser region, your lambda is changing. So this whole subject is about your wavelength, change of the wavelength. So when you are in a particular wavelength, you go into a denser medium, your light is dividing into different rays, and those different rays are generating just because the wavelength of the light is changing. Okay, so now you have phase constant, which is changes. Okay, these are few things. uh, any questions so far? Anything which is not clear in your mind, and maybe I just repeat it or explain it better? If nothing, just yeah.
Sorry,
So
just the very first equation that you wrote, that was the electric field equation, right?
this one,
Yes.
yeah, wave equation, yeah, electric field. So that was your question?
Yeah, that's it.
Okay, okay. Okay, yeah. So we are talking about the light going from one medium to another. So basically, when you are generating light in LED or in laser, you are going to put it inside the optical fiber. So we imagine that this source, which is your LED or laser, it's placed in air. So we consider n is equal to 1, but inside the fiber is some other material, so denser material, because we want to keep this light inside the fiber, so we make it denser. So it means we need to know what happens when light strikes the denser material and or it moves from one material to the other. So we go back to our very common concepts. I hope you have studied this, but must have forgotten. So I just revise them for next 5 minutes, and then we take 5 minutes break and move to the problem set. So now let's say you have this line. This is the, let's say, boundary of materials. Okay, if this is air and it has effective index n2, and that's any dense material, it could be glass or anything, water. Okay, and this light is coming out of the denser material and it comes here, and again it's paused. Give me just, yeah. So you have air and you have a dense material, and light is coming, going from this and reaches here. Now you have two options. Either this light is going to, not either, it is happening simultaneously. Some part of the light is traveling back, which we called a reflection, or it is going outside. This is your reflection. Okay, now we draw the I think when I write, I'm touching something and it just pauses everything. Sure. Yeah, so this part is reflecting and this part is going out but at a different angle. So now we draw a perpendicular on this point where light is striking. Okay, so this reflected light is making angle with this, and this light, original light, is making angle with this. Let's call this angle phi 2 and this one is phi 1. Okay, then we have Snell's law. Snell's law. And Snell's law says that, let's say this is N1. Snell's law says N1 sine phi 1 is equal to N2 sine phi 2. Okay. And we want to keep this light, all of the light, inside the fiber optical cable. It means we do not need this reflection part of the light. So what can we do? Any guesses? What will happen? What would be the condition that the whole light is reflecting back and not going out of the fiber optical cable? What will happen to phi 2? Is it going to increase or decrease if we want total internal reflection? Any guess? Like, just give me the wrong answer, but I just want you to get involved more.
Would it increase?
Yeah, it would increase. Why? Because let me draw. So you have light here and it's going out. So you want this to come here straight like this. Then you will have all the light going in. It means this phi 2 when become 90 degrees, it means the whole light is going inside. Okay, and you have total, see, forgot the spelling of total. So you have total internal reflection. It means phi 2 is equal to 90 degrees. Let's put in this one formula, N1 sine phi 1 is equal to N2 sine 90 degrees, which means this is called critical angle, this phi 1. It means that this angle you will have total internal reflection and the whole light is staying inside the fiber, not going out. Okay, I just wrote the expression. Let me just pause it and then I share. We will get the expression. Yeah, so this is your expression. Supposing it's number 5. So these are the 5 main formulas we are going to use next in the problem sets. So I give you 5 minutes, or you want more? Let's say,
can you scroll up a little bit? Thank
yeah.
you.
Yeah, so let's come back around. We have 8 minutes break. 8:55. We start again, and we will jump to problem set one, and we are going to use these formulas for that. In the meantime, I'm here. If you have any question, just call me and I'll unmute and answer. Okay. See you in 8 minutes.
Oh, I have a quick question about the total internal reflection.
Yeah.
Um, so it's about like how you would find your phi. Like I don't understand like the concept behind like the picture that you drew.
This one, which is on the screen right now.
Yes, oh, you mean like when phi 2 is 90 degrees, right?
Yeah.
Then what would happen?
So it means, that's the other part, this reflection part. Our target is
Mhm.
to keep it inside the denser material. Okay.
Okay.
And it means if we keep increasing this phi, or like whatever you call it, phi 2, uh,
Hmm.
if we are increasing it, we are bending the light towards the denser material, actually. And we keep bending it until the phi 2 is 90 degrees. So it means this is the maximum angle. After this, light cannot come out. We are not sure either it's traveling parallel to this boundary line or it's inside, but we are sure about one thing, it's not going out. So we say this is our critical angle, 5 1. This critical angle, we are pretty sure no refraction is happening. Got it?
Gotcha. Okay, that makes sense. Thank you.
Yeah. So yeah, no refraction is happening means we are supposing everything is inside, so it's called total internal reflection. The light is reflecting back, not coming out. Okay, so let's start with the problem set. I would say just open your problem set file, so I don't have to, read it. So problem set. Shall I start? Everyone is here. Hello, guys. Say
Yeah.
something. Yeah,
Hello.
yeah. When I ask, say something that I
Oh,
know.
sorry.
No worries. Okay, so the question number one. Question number one says, you have an electric field oscillating at some angular frequency omega, and its x component is 100 e raised to power j30, y is this, z component is this, and you can write the equation of this electric field as E is equal to again pause. Yeah, so you can write this equation of electric field as E is equal to 100 e raised to power j 30 degrees Ex plus 20 e raised to power minus j 50 degrees Ey plus 40 e raised to power j 210 degrees Ez, and this is multiplied by, this whole thing is multiplied by e raised to power j omega t. Express this as a measurable electric field at 100 megahertz. So it's, this question is very easy. I'm going to solve it quickly so we save time for other questions. So basically it's saying that expand this equation in nutshell. So we have our Euler formula, which says e raised to power j theta is equal to cos theta plus j sine theta. So let's multiply this e raised to power j omega t with this equation inside the brackets. So you will get 100 e raised to power j 30 degrees dot e raised to power j omega t ex plus 20 e raised to power minus j 50. Again, I paused. E raised to power minus j 50 dot e raised to power j omega t Ey plus 40 e raised to power j 210 dot e raised to power j omega t Ez. So when you multiply uh, this expression, basically you are adding the powers. So 100 e raised to power, this becomes j omega t plus 30 degrees Ex plus 20 e raised to power j is common, omega t minus 50 degrees Ey plus 40 into e raised to power j omega t plus 210 degrees Ez. Okay, so far it's easy. So now as I wrote the Euler formula, you convert this expression exponential form into cos and j sine theta form. So now I'm not going to use j sine theta part. Why? Because I explained we only need the real part of the equation. So we we need only real part of expression, so no j sine theta.
Why do we only need the real part of the expression?
So basically, okay, then I have to go to the math part, but I explain you. Let me know if you understand, otherwise I'll draw it. So when you have e raised to power j theta, so your equation has real part along the horizontal axis, and then the vertical axis is your j sine theta part, and the whole equation is real part plus imaginary part, and then you find something in the circle. Okay, I draw it, something
Mm-hmm.
like this,
Yes.
and then you have this imaginary part and then real part. Okay, and let's say you
Mm-hmm.
have a point here, so now you can not express it with cos theta only, you express it with j sine theta as well. But in
Right.
our case, we don't have any imaginary part. We express our light equation with only this real part. We don't need this imaginary part. So why we use it basically. So we ignore
Right,
this
because we only look at the electric field.
electric field real part. Okay, the
Okay.
cos theta part.
Okay.
Yeah.
Okay. Okay. That
So
makes sense.
it's in the book actually. It's given there in detail that how the magnetic and electric fields are moving. Ultimately, they cancel the imaginary part. Okay,
Okay.
so you can, yeah, see that. So that's why we don't need this imaginary part. So let's say I am converting straight. So we have 100 cos omega t plus 30 degrees ex plus 20 cos omega t minus 50 degrees ey plus 40 cos omega t plus 210 degrees. Ez. Okay, if you look at the problem again, read the last line. Express this as a measurable electric field at 100 megahertz. Okay, so this omega part is uh, this omega is equal to 2 pi nu, and put this in a equation above. Okay, so you have expression. What will happen? Yeah, 100 cos 2 pi nu dot t plus 30 degrees ex plus 20 cos 2 pi nu dot t minus 50 degrees plus, like you can write the third part. I'm not writing. Okay, so your nu is given 100 megahertz, so just put the value 100 cos 2 pi, so it's 100 megahertz. Megahertz is 10 to raise power 6, so it means it's 10 to raise power 8. Okay, dot t plus 30 degrees ex plus 20 cos, and you can write the whole expression. Okay, so that's it. The question was just asking that. Now we move to question 2. Question 2 says a wave is specified by this expression y is equal to 8 cos 2 pi, and then in brackets you have 2t minus zero point 0.8 z, where y is expressed in micrometers and the propagation constant is given in micro per meter. So it says find the amplitude, B the wavelength, part C is find the angular frequency, part D the displacement at t is equal to 0. So we just did this formula. E is equal to E naught cos omega t minus kz. Okay, I write it in this form, or y is equal to a cos omega t minus kz. Does it make sense? You can see. So first thing, amplitude. Amplitude means it's saying find E naught or A. So part A is amplitude. So what would be the value of A?
8.
8, yeah. So A is equal to 8. Part B, find the wavelength. Wavelength would be what? So can you tell me the formula? Like we wrote two, like 5 formulas. Which one you think involves wavelength? Let's write all of them.
I think it was the k is equal to 2 pi over
Good.
the wave.
Yeah, 2 pi
Mm.
over lambda, and this lambda is in micrometer, let's say. So it's saying find lambda. Yeah. So what would be the k? So we are finding lambda, which is now 2 pi over k. So can you see from the equation what should be the value of k?
0.8.
0.8. Perfect. So 2 pi, I wrote it right. Uh, Are you sure it's 0.8? Yeah, you got it. But is it 0.8 or you are multiplying it with something?
2 pi multiplied by 0.8.
Exactly. So basically you have this 2 pi outside. So when you make the equation, equate the equation, it has to be in this form, omega t minus kz. You multiply this 2 pi throughout. Okay. So this is
Okay.
2 pi over 2 pi dot zero point 0.8 multiplied by 0.8. So your answer is 1 over 0.8. So your lambda is, give me the value of lambda. Calculate it.
1.25.
So 1.25 what?
Micrometers.
Sorry. Yeah, we are finding lambda. Why did I write k? No. Micrometers. Sorry. In my notes, I wrote k is equal to 1.25. Sorry. Yeah. So what is the next part? That's A, B. C is find the angular frequency. Find the angular frequency. So angular frequency is your omega equal to what? Let me go up. So what was the expression for omega? Anyone? Even up.
Is it C times K?
It's, if you see here, can you see somewhere here? Omega is equal to 2 pi nu, 2 pi f. So omega is equal to 2 pi nu. And let's go back to this original expression. Y is equal to 8 cos 2 pi 2t minus 0.8 z. So our generalized expression is cos omega t. So it means omega is 4 pi. Do you agree?
Yes.
Yeah, because let me just write it down. Because we have expression y is equal to 8 cos 8 cos 2 pi. What is the expression? Cos 2 pi 2t minus 0.8 z. So it means it's 8 cos 4 pi t minus 2 pi dot multiplied by 0.8 z. So that's your 2 pi nu t. Okay. So what would be your omega? Or let's say nu. So your nu will be 2 and your omega will be 2 pi nu is equal to 2 pi into 2 is equal to 4 pi. Okay. Is it clear? No? Do you want me to repeat? Just let me know. Something in chat.
Why won't omega just be 4 pi?
Yeah, so basically we are following this expression, generalized one. Okay, E is equal to E naught cos omega t. Okay, and omega is 2 pi nu. Then we equate this expression with this given one, this one. Okay, and we saw that we have not omega t but 2t. Okay, so it means your, got it?
Yeah.
So 2 into 2 pi, 4 pi. So it's saying find omega. So it, you can straightforward find it. Okay, like I'm equating it's 4 pi and I equate omega, instead of omega I have 4 pi. So omega is equal to 4 pi. Or you can calculate like this.
Okay.
It's up to you. Okay, what is the last one? D part. Find the displacement at t is equal to 0, time 0, and your distance is 4 micrometer. So let's put this y is equal to 8 cos 4 pi, t is 0, and this is your 1.6 pi into 4 micrometer. Okay, so that's 8 cos of minus 6.4 pi. 8 into, so I'm just doing it quickly, so we should spend more time on the other question. Next 1, 2, 3 questions. Okay, so this one was straightforward. You were given z at t is equal to 0. You put both values and you get your answer. Okay. Now, question 3, I would encourage you to solve and tell me the answer. Question 3 says, what are the values for the energy in electron volts, frequency in hertz, and the propagation constant k of light at wavelength 820, 1320, and 1550 nanometer? Okay, one more thing. In next lecture, professor will explain these are the main 3 wavelengths which are important for our subject for optical communication, in fact. So because the light we generate are on these 3 frequencies. So he'll explain what happens at 820, 1320, and 1550. So mostly in this subject, you will also see these 3 wavelengths a lot of time. Most of the questions are revolving around these wavelengths. Okay. So it says, let's say part, uh, part A says find, it says 820 nanometer. So first thing we will do, we will convert it into 820.820 micrometers. Okay. Now it says find energy, find uh, frequency, and find propagation constant. I want you guys to calculate it and tell me, and then I see if it matches with my.
Can you just scroll a bit up or like scroll down a bit?
Up or down?
So that's
This?
yes, it's good now. You can scroll back.
Don't pause. I think I'm figuring out what is happening with this pause thing. So till next lecture, we'll be fine. So just write EG so you won't confuse it.
So for A, the EG that I got was 1.5 electric volts.
Correct. Yeah. I got 1.512.
Yes, I just left out the last
E
decimal.
is equal to 1.512. Yeah. Okay. Now what about
And then
frequency? So
I got 3.65 times 10 to the 14.
and formula you used was, sorry, 3.6. Yeah,
3.65 times 10 to the 14.
correct. Yeah. So formula we are using is C over 1. And your answer is 3.65 10 to the power 14 hertz. And for K, the formula is 2 pi over lambda.
Yes, and that for that I got 7.66 times 10 to the 6.
Correct. Per micrometer. Okay. So in this subject, when I studied this subject, my professor was same professor. So I just let you know that he is quite what you say is very touchy about these units and converting wavelength into microwave. And then in next lecture he'll explain you that you are not going to use a unit for light as meter per second but kilometer per second. So focus on those small things. when you are taking the lecture, just focus on those small things which he's explaining and go through all the slides. So if you go through all the slides in detail, like memorize them, understand them, and do the tutorials, you will get really good grades because he's very lenient with marking. Like I can assure you, when I studied, he was lenient. So yeah. So similarly, you can solve it for all the frequencies. Like you have, so here you have this part B is about lambda is equal to uh, 1320 nanometers. So which means lambda is equal to 1.320 micrometers, and then you can solve it. Okay. So when I post the solution, you will get all the answers. Okay, everything solved. Like not solved on this, what I'm solving right now, I will post it as it is. But the proper solution which professor will post, he'll post all the answers. Okay. Let's move to question number 4. And then we have question number 5 and 6. Yeah. Question number 4. Tricky one.
Also, is it a rule that the prof wants the K to be divided by micrometers?
You mean when you find k, 2 pi over lambda?
Yes, like your final answer, because for that question, like it was 7.66 times 10 to the 6.
Uh, yeah, so you see, I wrote micro with it. So how did you solve it? 2 pi over what lambda? You solve it.
Oh, yeah, no, like I put the 2 pi over lambda with the correct units, like the 0.82 micrometers, and then that would cause this to be 7.66 times 10 to the 6. But he's like,
Yeah.
what my question is, do you want the K to be divided by micrometers?
So what we did, we never took the chance, and we never wrote 10 to the power minus 6. We just put micro. But
Okay.
he'll not object because you are writing 10 to the. So if you write 7.66 into 10 to the power minus 6, and then you write per micrometer, then it's wrong. Yeah, but if you write
Yes.
7.66 10 to the power minus 6 per meter, then he won't cut any marks. Okay.
Okay.
Okay. Question number 4. Question number 4 is important and interesting, so it will challenge you a little bit. So it says the electric field of a light wave is specified. Can we go to the separate? And that's fine. Question number 4. So electric field of a light wave is specified by E is equal to 10 cos omega t minus beta z. So this beta and k both are phase constant. So he took this question, I think, from a separate book. So he used beta instead of k, but it's same thing. Okay. So where E is expressed in microvolt and the propagation constant is given in micro per meter. Per micrometer. The distance z is measured in micrometer. The wavelength is 1.5 micrometers. So your wavelength lambda is given as 1.5 micrometer. Find the following parameters with appropriate units in air and in glass. Refractive index are given. Okay, for air n is equal to 1 and for glass n is equal to 1.5. And give the answers in terms of pi. Then he gives you one hint. Hint is the relationship between omega and beta can be measured to be omega is equal to 3 beta square. To calculate the group velocity, we will see that calculate the group velocity
Is that relationship true all the time or just for this question?
for this question. So he can change it, but if he changes, he'll give you that
Okay.
expression. Okay. So now it says, okay, find the wavelength in air. Let me draw this. So I'm just writing the that's air wavelength. You have frequency, and then you have omega. It's being paused. Yeah, so you have wavelength, then frequency, radiant frequency, omega, propagation constant, and then you have your VP and VG. So air, N is equal to 1, and for glass, N is equal to 1.5, and then it says write the units and units. So what is the wavelength in air? It's already given. The wavelength is 1.5 micrometers in air. So let's write 1.5 and micrometer in the units. What will happen with the glass? So let me write this down for you. So this is actually lambda over n. Okay, so your n is 1, so wavelength is not changing. But when you come to the glass, your n is 1.5. Okay, now what will happen to the wavelength? What is the wavelength? 1.5. You divide it with 1.5, so you get 1, and unit is micro. So your wavelength is changing. Okay, when you're moving from one medium to the other. Now what about the frequency? What is the formula for frequency? Anyone? Your formula for frequency? C is equal to F lambda. So F is nu. So which means nu is equal to C over lambda. Okay. And it means 3 into 10 to raise power 8 divided by 1.5 into 10 to raise power minus 6. And your answer would be, let me tell you, 200 terahertz. Similarly, for glass, your formula is C over n lambda. Let me put n here as well. So C over n into lambda is, sorry, C is 10 to raise power minus 6, which means your frequency again is 200 terahertz. Make sense? So your frequency is not changing, as I said. How about the angular frequency? Angular frequency is 2 pi nu. So you just multiply and you get 400. He said put your answers in terms of pi. So whenever you have pi, don't touch pi. And you have 400 pi into 10 to the raised power 12 radian per second. Similarly here, you have 2 pi nu 400 pi into 10 to the raised power 12 radian per second. What about the propagation constant? What is the formula for propagation constant? 2 pi over lambda?
Yes.
So, okay, when you have your quiz, or just ask your professor that is he going to give you the formulas? If he's going to give you the formulas, or if he allows you to keep the cheat sheet, formula sheet, then you don't have to memorize. So ask him well in time that either you are going to memorize these formulas or you can keep them with you. So that way you can focus more on solving it, the questions, and don't worry about the formulas. Okay. So 2 pi over lambda, let's say that's your beta naught. You will get 4 pi over 3 into 10 to the raised power 6 per meter. So see, now I'm not writing micro with it, okay, or mega with it, or anything, just per meter. Okay, in terms of glass, your beta glass is your refractive index of glass multiplied by your beta naught. When you multiply it, what is the answer?
I think it's paused again.
Come on. Yeah, so I just said that for the phase constant in glass, you have formula refractive index of the glass multiplied by the phase constant in the air. So what would be the answer? Just multiply them and you will get 2 pi into 10 to raise power 6 per meter.
I have a question about nu for the air. So that one is 200, but then for glass, when you have the 1.5 times 1.5 in the denominator, that changes the output of nu.
Of nu, okay. So 1.5 into 1.5 is
2.25.
let me see, yeah, maybe I did a mistake here. Then multiplied by, so that's 133. 1.5 into 1.5, then you have 3 divided by 1, so 1.33. Sorry, my bad. Thank you so much. So basically I did mistake here.
It should be 1, right?
It should be 1.
Right. Okay.
So let's say this is n glass. Thank you.
No worries.
So now phase velocity. What was the formula for phase velocity? Formula for phase velocity.
It's omega over k.
Omega over k.
Yeah,
and yeah, both are
and
c over.
c over n.
Yeah. So you will get same answer, but I'm using c over n. Okay, so your phase velocity is 3 into 10 to the raised power 8 meter per second. Let's find for the glass. C over n glass is 2 into 10 to the raised power 8 meter per second. So you see the velocity is changing when you are going from lighter medium to the denser medium. So two things are changing. Phase velocity is changing, and then your wavelength is changing. These two are very important. What about the group velocity? So formula for group velocity was delta omega or curly omega. It's up to you, whatever you say. I call it curly omega. And the expression, what was the expression? Can you see the problem again? In the hint, it says the relationship between omega and beta can be omega is equal to 3 beta squared. It means curly omega or curly beta is equal to, let's take the derivative, and it's 6. Yeah, which means it is 6 into 4 pi by 3 into 10 to the raised power 6, the value we found. Okay, meter per second. What happened here? You have curly omega curly theta is equal to 6p. So Vg is now 6 into 2 pi into 10 to the raised power 6, 12 pi, and units are meter per second. So we are done with 4 questions. Now we have 20 minutes and 2 questions.
Does the ng for the group velocity always 1?
Sorry?
Because the another formula for like the Vg is c over ng, right?
Yeah.
So my question is ng always 1?
No, not particularly.
Okay.
So it's the ng. G signifies the group, and then you have to see the medium for the n. So n and g.
So just to solve it in this case, you just take the derivative.
Yeah.
Of,
so I didn't need the
of
So
the angular frequency with dB, right?
Yeah. So I can do it straightforward with this expression.
Okay.
So group velocity. Sorry. I think the formula for phase velocity is c over n. So group velocity. Let me see.
Because I think you wrote that it's c over ng as well.
Yeah, in his notes it's C over ng, but the ng is the group velocity refractive index. So I think that would be given to us, right?
Only if it is given, plus as expression it's same, like Vp and Vg are same, but when we calculate it, these two things are very different. Let me just so basically, let's say you have this bigger wave, something like this, and you have these small, like this envelope is made of these small frequencies, okay, or different waves. So when we talk about group, this is different. Let's say this is F1, this is F2. And we talk about the group, we take it as a group. This thing is your Vg now. So we prefer this delta omega over delta beta, okay? and this only frequency is your VP. Like every single uh, frequency, the speed of this each ray is your VP, phase velocity. So when you have monochromatic light, you only have this one wave, nothing inside, okay? So you say, okay, we are going to use VP. So if you remember, professors say that at one point VP is equal to VG. So if you calculate VG is equal to C over N, it means ultimately you are saying that VG and VP are same. Does it make sense?
Yeah, but is the formula still C over NG? Is NG its own refractive index for the group wave or no?
Yeah. So you will calculate it for group wave,
Okay.
but then when you have the answer, you will say that this is equal to VP. So why we are calculating VG actually? So like it's complicated, but yeah, it's same thing. You can calculate C over NG, but then you will say, yeah, it's the same expression as VP or same answer as VP. But here you won't get the same answer. Like here you have more rays. You already know that you are in a denser medium. So they are different. Like it's very confusing, but it all depends on your sense. Like either it's gonna be same, so I can use C over NG, or you intuitively know that, oh no, it's not gonna same, so I have to use this delta omega or delta beta expression. So I would say for the course, whenever you find VG and you are given the expression like um, this expression, what was the expression? I forgot. 3 beta square, omega is equal to 3 beta square. Use that. Don't use C over NG. Okay.
But the VG would be the same, right? Obviously for both of them as well. For the
Uh,
glass and for the air.
no.
Oh, so it's different.
It's different. So
Okay.
that's why, because it's dependent on the value of phase constant. That's why when you are in the air, you have expression 4 pi by 3. But when
Oh,
you're
okay,
in
I
the
see.
dark, you have expression 2 pi by 2 pi multiplied by 10 to the power 6.
Okay, because I always thought the group velocity was the same, but okay.
Yeah, when they are same, it means you are talking about just one ray, not the group of rays. Okay.
Okay.
So let me remove this. Question 5. Light traveling in air. Let me see what question 5. Light traveling in air strikes a glass plate at an angle theta 1 is equal to 33. So the theta 1 is measured between the incoming ray and the glass surface. So let me just draw it for you. So it says that this is the surface or the boundary between air and glass. Obviously for air n is equal to 1, and for glass we don't know yet. So it says that light traveling in air strikes a glass plate at an angle of 33 degrees. So light is traveling in the air and it strikes, light is traveling in the air and it strikes the glass. So we draw this perpendicular. It says the light is striking at angle of 33 degrees. Upon striking the glass part, upon striking the glass, part of the beam is reflected and the part is refracted. So some part it says is reflecting and some part is reflecting. Okay. If the refracted and reflected parts or beams make 90 degrees with each other. So this is your reflected part and this is your reflected reflected part angle. And it says that let's say this is theta 1, this is theta 2. So these two angles are equal, this theta 1 and this one. This is also theta 1, 33 degrees. So reflected angles are always equal. Okay. So it says theta 1 plus theta 2, reflected angle and refracted angles are 90 degrees. What is the refractive index of the glass? So what would be N glass? And what is the critical angle of the glass? Theta C of glass will be what? Okay. Now what should we do? For part A. If we have theta 1 plus theta 2, but we don't have this particular, like theta 2 is what? Any guesses?
57, because 90 minus 33.
So theta 1 plus theta 2 is equal to 90. So it means theta 2 is equal to 57. Let's say theta 2 is equal to 90 minus 33, 57. Now we have this. What is the what does Snell's law says? Snell's law. We just wrote the formula. It says
N1 cos theta 1 is equal to N2 cos theta 2.
N1 sine, but that was not theta, that was phi. Remember? What would be the phi 1 and phi 2? Which angles are?
Wouldn't it be 90 minus theta?
90 minus what? Sorry?
90 minus theta?
Theta 1?
Yeah.
Yeah,
Or
so that's
phi
your
one.
phi and that's your phi 2. Okay. So basically angle with the normal. So your Snell's law formula was your sine. Phi 1 means angle with the angle you are making with the normal. So if this whole thing is 90 degrees, it means phi 1 is 90 minus 33, N1 sine 57 degrees. And what would be your phi 2? So theta 2 is 57. So it means this is your 33 degrees. Let me just write down again. Yeah, so one is 57 degrees. Okay, so it means this is your 33 degrees. So N1 is your, let's say, glass. That's 1 into, I think it's 0.838. And this is your N2, which is your N glass. And this is 0.5446. So your N glass is 1.54. How about the critical angle? What is the formula for critical angle? Hello? Anyone?
Can you explain what the critical angle is again?
So the critical angle was where you have total internal reflection. So this refractive part, this this straight line which is going inside the glass is totally reflecting back. So basically, what does it mean? If you see it other way around, let me go to the main equation to explain. Yeah, so if this is your reflected part, it should come 90 degrees, that you have total internal reflection there. Okay, for total internal reflection, this angle is your critical angle. What would be this angle when you have total internal reflection? So let's move to, come on, chat.
So would it just be 40.5 degrees?
Exactly. Very nice. So sine inverse of n1 over n2. Okay, one trick I tell you, that all you will have always the lighter refractive index above and the denser was in the denominator. So that's your air. Even if you get confused and you start putting in the formula and you're confused, either it was like which one will go in denominator, which one will remain in numerator, just remember that n1 is always the lighter one. So 1 over 1.5, 40 point was the answer, 40.5 degrees. Okay. So that was the question. Now, last question, we have only 7 minutes. So let's do it quickly. So a point source of light is 12 centimeters below the surface of a body of water. So let's say if this is your body of water, it says the light source is 12 centimeters under the surface or below the surface. What is the radius of the largest circle on the water surface through which the light can emerge? So this light is going everywhere, here, here, here. It says what is the radius of the largest circle, like the point after which basically light is coming back. What is the last point? I can put it this way. What is the last point from where the light is going out? So what is the radius of the largest circle on the water surface through which the light can emerge? Okay. So if we say this is that point from where light can emerge, and after that you have total internal reflection, it's saying, it's asking you to find the radius. Okay, and then it says n is equal to 4 by 3 for water. This angle and this angle. So it means this is your critical angle. Okay, after this angle, you have total internal reflection. This is the last point from where light is emerging up. After this, you have total internal reflection. So your theta C is sine inverse of n1 over n2 Again, yeah, n1 over n2, which means sine inverse of the lighter material's refractive index divided by the denser materials. So your theta c is equal to 48.75 degrees. So now our target is to find r. What would be r? Can you tell me in terms of the angle, like if I divide r by 12, what would be the, in terms of trigonometry, like if r divided by 12 is equal to, let's say I tell you, I don't have time, is theta c. Okay, r divided by 12 is theta c, which means r is equal to 12 multiplied by tangent of theta c. That means r is equal to 13.7 centimeters. Okay. Clear? Any questions?
Can you scroll down?
Next time, I think you guys will study about the fiber optic, like what happens inside the fiber optical cable. You will have formulas and you will do the problem set too. I think it's one day
So
before the quiz. Yeah, sure. Go ahead.
I just had a quick question about like group velocity that we were talking about earlier.
Mm-hmm.
So you know how you said that the group velocity, like one of the formula was C over NG.
Mm-hmm.
So NG is equal to N only when you're talking about a single wave, right?
Yeah, single
But
wave.
otherwise,
Uh, don't say wave, just array or
okay,
one wavelength.
okay, one wavelength. Okay.
Yeah. When you do the fiber, professor will explain that. So you have multiple rays going inside the fiber optical cable, and each ray has a different velocity. It's not traveling on the same velocity, like in the air in vacuum when you have 3 into 10 to raise per 8 meter per second. One ray will have velocity like 2.1 into 10 to raise per something. Other will have 2.2. Third one will have like 1.2. So they are reaching their destination at different times because of different velocity. So we cannot pinpoint that, okay, like phase velocity for this ray is this, for that ray is. What we do is we make an envelope and we calculate the velocity of that envelope. Inside that envelope, you have all these different wavelengths or frequencies. So you said the velocity of the group is this. Does it make sense?
yes, yes, which is why it makes sense that the NG would be a value that's either given, um, right. It would
Yeah,
be given, or you would just use the delta omega over
yeah. But
delta
when
beta.
when that's what I was saying, that when ng is given and you calculate Vg,
Mhm.
ultimately you are saying that Vg is equal to Vp, because formula for Vp is also n over c over n.
Yes.
Yeah? But when you don't have ng, so you go for that expression, the derivative.
Okay. Gotcha. Yes, that makes a lot of sense. Thank you so much.
Okay, then see you not next week, after that. That's how it's working. Yeah. Anyways, have a nice day. Let me just end the meeting.